Have you ever wondered if the laws of our universe are just a cosmic accident? Or is there something deeper, maybe a hidden geometry, dictating everything from the ground up? Well, today, we're diving into a really radical idea that might just rewrite our entire understanding of reality. All right, so let's get right into it. For basically a century now, physicists have been haunted by this handful of numbers. They're these fundamental constants that seem, perfectly dialed in for life to even exist. But where did they come from? Why these specific values and not something else? Okay, take this one for example. The inverse fine structure constant. It's this number, roughly 137, that basically controls how strong electromagnetism is. And here's the crazy part. If you change it even just a tiny bit, stars couldn't shine. Atoms wouldn't even hold together. So the big question is, why 137? Why that number? Or how about this one? The whole matter-antimatter thing. Back at the beginning, for every billion particles of antimatter, there were 1,000,001,000 particles of matter. And that 1 in a billion left over, that tiny fraction is everything. It's you, me, the stars, everything we see. It's an incredibly specific number, and so far, we have no idea why it's like that. And then, of course, there's the really big one, dark energy. It turns out that something like 68% of everything in the universe is this mysterious force that's pushing space itself apart, making it expand faster and faster. And again, you have to ask, why 68%? Why that exact amount? So, the standard view in physics is that there really is no view. These numbers are just treated like fundamental inputs. We measure them in experiments, we plug them into our equations, and hey, they work. But it's not very satisfying, is it? It kind of suggests we just live in a universe built on pure random chance. But what if that whole idea is just wrong? Well, there's a pretty radical new theory that says these numbers aren't random at all, not even a little bit. It proposes they're the inevitable result of the universe's most fundamental structure, which isn't a smooth, continuous space like we usually imagine, but get this, a discrete, living geometric lattice. Okay, so let's break that down. The standard picture of spacetime is like a smooth, continuous fluid. You can zoom in forever. But this new idea, it's totally different. It says reality is more like a crystal. It's built from a lattice of the simplest possible 3D shape, the tetrahedron. Now, I know what you're thinking. That's a huge claim. So where's the proof? Where's the evidence? Well, believe it or not, the first major clue has been hiding in plain sight for decades, buried in the faint afterglow of the Big Bang. So when we look at the cosmic microwave background, that baby picture of the universe, we see something really, really strange. The little hot and cold spots, the temperature patterns, they're correlated all across the sky, but only up to a certain point. The moment you look at two spots separated by 60 degrees, poof, the correlation just vanishes completely. It's the super sharp, totally unexplained cutoff. In that number, 60 degrees, it's not random. It's the interior angle of an equilateral triangle. And what's an equilateral triangle? It's the face of a tetrahedron. So the theory says this isn't some ancient echo from the Big Bang. No, it's the fundamental structure of space itself, right now. The reason we can't see correlations beyond 60 degrees is because we're literally looking at the edge of our local pixel of reality. Okay, so if reality is this geometric lattice, how does it get built? Well, the theory proposes it's a dynamic process. The Big Bang wasn't this one-and-done event billions of years ago. It's a continuous transformation that is happening right now, everywhere, all the time. And this mechanism has a name. It's called the Jitterbug. The idea is that there's this constant rhythmic collapse of pure, unstable potential into the stable geometric structure of reality. You can almost think of it like the ongoing heartbeat of the vacuum. And this diagram really shows us how it's supposed to work. So reality starts as this state of pure, unstable potential. The theory calls it vector equilibrium. Now, to become stable, it's got to collapse. But look, it can't just shrink straight down. It's forced to twist as it collapses, choosing a direction, a handedness, left or right. So that's the crucial part, right? It's this three-step dance. You go from pure potential, through a forced twist, and you end up with the stable tetrahedron. And this one, single, continuous move is what's building the very fabric of spacetime. And, as we're about to see, it's what sets the rules for pretty much everything else. Okay, so this is where it gets really interesting. How does a simple geometric dance create those fundamental constants we talked about? How on earth does a simple collapse and twist explain a number like 137?
Well, it all starts with a universal principle, efficiency. Think about how nature packs seeds in a sunflower head. To minimize energy and repulsion, it uses something called the golden angle, which happens to be about 137.5 degrees. This is just nature's ideal, most efficient way to pack things. And the theory says the vacuum wants to arrange itself in this same ideal way.
But here's the catch. Here's the problem. Nature's ideal angle, that 137.5 degrees, is based on the golden ratio, an irrational number that goes on forever. It has infinite digits. But physical reality can't be infinite, right? It has to be quantized. It's pixelated. Think of it like a guitar string. A guitar string can't vibrate at just any old frequency. It can only vibrate at specific harmonics that make a clean note. In the same way, the universe can't support an infinite, irrational rotation. So it's forced to make a compromise. It has to snap from the ideal 137.5 degrees to the nearest stable, allowable harmonic. And what is that number? 137.036. And that tiny little difference, that leftover fraction of a degree between the ideal and the real, that's not just a rounding error. That little bit is everything. This is what the theory calls geometric strain. It's the unavoidable imperfection that you get when you try to cram an infinite ideal into a finite physical reality. So here it is. Here's the big reveal. The fine structure constant, that magic number 137, isn't some random dial setting. It is the literal measurement of the vacuum's structural compromise. The electromagnetic force itself is the tension created by that geometric strain. It's the price the universe has to pay for being able to exist in a finite, quantized form at all. But wait, it doesn't even stop there. What's truly mind-blowing is that this one single principle, this geometric strain, might also explain the biggest mysteries in the entire cosmos. Okay, so picture space-time like one of those tensegrity structures with rods and elastic bands. In this model, matter, what we're made of, is just a spot where the lattice is compressed and twisted into a kind of knot, crimped at that real-world angle of 137 degrees. And that compression, that puckering of space, is what we experience as gravity. But here's the thing about tensegrity. For every compression, you have to have a corresponding tension. And that tension, that's dark energy. It's the elastic recoil of the whole lattice, constantly trying to spring back to its ideal relaxed state of 137.5 degrees. They are literally two sides of the exact same coin. And get this? This isn't just so cool-sounding analogy. This model makes a stunningly precise prediction. Based on nothing but the geometry of this compression-tension relationship, it calculates that matter should make up 31.8% of the universe's energy budget, and dark energy should be the remaining 68.2%. And those numbers? They are an almost perfect match for what our best cosmological measurements actually show. So what's the big takeaway here? It's that the fundamental numbers that govern our reality, they might not be random accidents at all. Instead, they could be the echoes of a deep, fundamental geometric struggle, the tension between the infinite perfection of an idea and the finite constraints of physical reality. It suggests we live in a universe built not on random chance, but on the beautiful and, yeah, slightly imperfect geometry of existence itself.